Right, well, this is a revision seminar about upper and lower sums for both Maths 1A and the course AQMF, and after there will be a request session for Maths 1A, because AQMF has already had theirs. So, most people are not so much confused or just feel like there's a lot of stuff in upper and lower sums. So, I just wanted to talk it through. And if you've got any questions, just put up your hand. If I do something wrong, please tell me, because we don't want that to propagate. So as an example, I'm going to use the example that already exists on the Maths 1A page in the Maths Learning Centre website, which is this. And there is a video of me doing it on YouTube already, but it might make more sense to see it on paper here. So, all right. Right. So my example is going to go like this. So find upper and lower sums U5 and L5 for f of x is equal to 2x cubed minus 6x squared plus 7 on the interval -1, 3. Okay. And using use the fact that the turning points are at x equals 0 and x equals 2. Okay, so that's the example. So we're going to find upper and lower sums, the fifth upper and lower sums for that function on that interval, using possibly the fact that the turning points are at 0 and 2. Okay, so the steps in finding any area using upper and lower sums are the same regardless of whether you're going to use it, whether you're going to find a particular one, U5 and L5, or whether you're going to find a formula for it in terms of n. So this is what we're going to do. So that's the question. So the first step is to divide your interval into sub-intervals. Okay, I'm dividing into 5 because I want U5 and L5. If I wanted UN, I'd divide it into n sub-intervals. And then once I've divided it into sub-intervals, I need to know how wide each sub-interval is, and in fact where each sub-interval ends and begins. So the width of each sub-interval, which is what is normally called delta x, is the width of the big interval divided by how many pieces you're cutting it into. So I'm actually going to write it here. Total width, because the total width has been cut into 5 pieces. The total width, of course, is 4 here, because you can do it as 3 minus 1 if you like. (4/5). And because we're really just approximating an integral, it's perfectly appropriate to use decimals rather than fractions in this situation. Okay, so it's perfectly okay to say that that's 0.8. If I was doing it with n, and I will do an example involving n, it would still be a formula. Okay, so since I know that I'm doing exactly 5, I can just figure out where the ends of all the intervals are. So the endpoints of each interval are, well, there's -1, that's the beginning. And I need to go 0.8 from there, so that's minus 0.2. I need to go 0.8 from there, so that's 0.6. And 0.8 from there, which would be 1.4. And 0.8 from there, which would be 2.2. And 0.8 from there would be 3. So that's my 5 intervals. From here to here is interval 1. From here to here is interval 2. From here to here is interval 3. From here to here is interval 4. And from here to here is interval 5. Note that to get from -1 to the end of the third interval, I have to go 3 lots of 0.8. Okay, so technically I could have figured them out saying that 1.4 is -1 plus 3 lots of 0.8. So the end of the third interval is 3 times the width away from here. But I'll do that again when we're doing it in terms of n. Okay. At some point, I have to draw a quick sketch of my function so that I know what's going on with it. Let's have a bit more space. Okay, and I've been told that my function is a cubic. Its turning points are at 0 and 2. Okay. I wonder where it goes. And being a cubic, it sort of has to have like a swoosh like that of some sort. So probably doesn't matter where it crosses the axis, and I don't actually know. So it's going to be something like that. I don't actually know what it looks like, but that'll do. Okay, I do know that the turning points are at 0 and 2. Okay? I'm going to actually have to figure out what the heights are at all of these edges. So I probably should have done that first, but at least I've got an idea of what it looks like. So my intervals are here. So that's minus 0.2. 0.6, 1.4, 2.2, and 3. Awesome. So what is going to happen is I'm going to cut it into pieces. Like that. I actually have no clue if it even goes below the x-axis, so it could all be above the x-axis, but it wouldn't make any difference because the location of the x-axis is irrelevant. It's where these lines are. Cool. So now to figure out the upper sum, I need to figure out where the maximum is on every interval. So I'm going to draw a table. Okay, so interval number 1, 2, 3, 4, and 5. And the location of the maximum. So on interval number 1, the maximum is here at minus 0.2. And on interval number 2, the maximum is here at 0 because the maximum is somewhere in the centre. And on interval number 3, the maximum is here at 0.6. And at interval number 4, the maximum is at one of these two ends. I don't know which one, so don't know which one it is yet. And at interval number 3, it's definitely at this end. If it goes up at that end, so it must be at 3. I don't know which one of these it is because it turns in there, and I don't know which end it is at. I'm presuming it's probably at the 1.4 because the turning point's closer to this edge, but I can't tell yet. So, and now I need to find the value of the maximum. And so to find the value, I sub this into my formula. Has someone got a calculator? Because I'm going to need one. If I can borrow. So what was my function? Okay. So 2 times x cubed minus 6 times x squared plus 7. So 6.7 when I sub that into my formula. And now that I've actually done my show of calculating it by hand, I'll go to my pre-prepared answers and tell you what the rest of them are. So I'll go a couple more decimal places. If I sub in 0, it comes out to 7. Just need to figure out what both of these ones are. So if it's at 1.4, then the answer is 0.7. And if I put instead 2.2, the answer is negative 0.7. So obviously not that one. Okay. And the final answer, this is 7 as well. So I've subbed in this one I wasn't sure where it was, so I just figured them both out and it wasn't that one. And so that's the value of the maximum. And to find the value of the upper sum, I'm going to have to add them all up, times by the width here, and that's the answer. So U5 is the delta x times these things. And the delta x was 0.8. So that's all been rounded off. If I was using a calculator, I would of course keep all the accuracy inside my calculator. But that's my upper sum. And the lower sum would be calculated in the same way, but I have to figure out where the minimum is on each interval instead. And I think I'll skip that bit. All right. Okay. So that's in general how to do it by hand. I wanted to use this example because you need to know that you have to make the choice of where the maximum and where the minimum is for every single interval separately. That choice has to be made. Okay? The thing is that you are often given functions where the choice is always the same for every interval because the function's increasing or decreasing. I'm going to show you one of those too. So my next example upper and lower sums with n equals 6 for f of x equals 3 dx to estimate the area under y equals 3 dx on the interval from -4 to 2. Okay? So I want to show you one more time. So this one, it's the same process again. So we're going to divide the -4, 2 into 6 subintervals. Always the first step. The width of each one is the delta x, which is the total width, which is 6, if you like 2 minus -4, on the 6, which is the n, which is 1. Okay, so my 6 subintervals will begin at -4 and will go up by 1 each time. So my subinterval endpoints are -4, -3, -2, -1, 0, 1 and 2. 1, 2, 3, 4, 5, 6 intervals in total. Okay? And then each of... Right. I'm supposed to draw a picture in order to figure out what's going on. And e to the x, 3 to the x looks something like that, where this is 1. And I've got my intervals here. And I want this area. But this function is increasing, so the maximum is always on the right-hand side, and the minimum is always on the left-hand side. So I don't have to make a decision for every interval one at a time, because it doesn't turn inside any of my intervals. So I can just say, for my table, I can say location of the minimum is the left-hand side of the interval, and the location of the maximum is the right-hand side of the interval for every interval, because it's increasing. So I should probably say before that, since f is increasing. So this time I'll do the lower sum, just so that you can see it. So to do the lower sum, I've got my intervals, 1, 2, 3, 4, 5 and 6. And I've got the location of the minimum. Well, the minimum is always on the left-hand side, so the left-hand side of interval 1, can't see, is -4. The left-hand side of interval 2 is -3. They're the left-hand ends of each of the intervals. I just have to sub it into into the formula. So the value of the minimum, it would be 3 to the -4, 3 to the -3, 3 to the -2, 3 to the -1, 3 to the 0, and 3 to the 1. And these are all whatever they are. Okay, so the value of the lower sum is the delta x times the sum of these things. Now I haven't written it up to this point, but I want to do it now so that I've flagged that it's a possibility. The sum from I equals 1 to 6 of the minimum value. So small m for minimum and big M for maximum. And it goes from 1 to 6. So that this I is referring to these numbers 1 to 6 here. It's telling you which interval you're in. And this mi is referring to what's in this column here. So that's I, all of these numbers, and this is the little mi. Okay? And so the delta x was 1, and the sum of those was these things here. Which will come out to whatever it comes out to. .5 approximately. I'm sure that's rounded off because this calculator seems to be always giving me 1 decimal place accuracy. Is that right? Okay. Much better. That's better. So your calculator's fixed now. Right. If I was doing the upper sum as well, I'd just add two more columns here, the location of the maximum and the value of the maximum as well. Okay? It's really important to keep in your head the concept that you have to know where the maximum is. Because if your function isn't increasing, you'll have to make a decision. If it turns somewhere, then the maximum will be where the turning point is. So you need to keep that in mind. Because it's not uncommon for lecturers to give you one where it does turn. If they're only giving you like L2 or L3 or something, they might do that to you. Okay, so the next question is, well, what would you do if you wanted a formula for what this would come out to for any number of intervals, which is what we do a lot in Maths 1A for a whole week or two, where you just get so sick of it because it goes forever and ever. In AQMF, you talk about trying to figure out exactly which n to choose to get your error as low as possible. Pardon me. So those from AQMF, if I do something now that doesn't sound familiar in your lectures, please just disregard it, because I'm in Maths 1A mode at the moment. Okay, so let's do another example. I haven't done the whole of this, but I don't want to go on forever. So my other example will be one of the classics. So find un and ln for the integral from 1 to 4 of 2x plus 1 dx. That's a classic. So un and ln are approximations for integrals. You've learned other approximations like the trapezoidal rule as well. And the trapezoidal rule, if you're going to calculate it, you would do exactly the same thing here, but you don't use the location of the minimum and the maximum, you just use the two endpoints. And you calculate a value for what's the average value is on that interval. Gosh, that'd be so much better. I'll have to tell that to the lecturer next semester. So, don't worry about that. It's part of my job to try and make sure that the lecturers do a better job. Doesn't always work very well. And every so often I have ideas. So we're going to find un and ln for this. So that means we're going to do exactly the same thing that we would always do. Our interval is from 1 to 4, so our interval is from 1 to 4, because that's what the integral is, and I'm going to divide that into n subintervals. And the width of each is my delta x. And this width is 3, 4 minus 1, and I have to divide that by n, because I'm dividing into n pieces. I don't know what n is, so I have to leave it as a formula. And now, just like with the others, I want to find where the endpoints of all the intervals are. I need to know where the left end is and where the right end is. So, because I can't just list them, I have to actually find a formula for it. So the right-hand side of interval number I. Okay, so to get to interval number I, you start at the beginning of the big interval. So you start at 1. Yep. And to get to the end of the first interval, you'll go one lot of the width. So my concept here, my picture that I'm drawing, goes like this. Here's 1, and here's 4, and I'll go one lot of delta x to get to the end of the first interval, and I'll go another lot of delta x to get to the end of the second interval, and so on. So the end of interval number I will be 1 plus I lots of delta x. That's how to get to the end of that interval. And so that will be 1 plus I times 3 on n, which is 1 plus 3I on n. Okay? Cool. And the left-hand side will be the end of the previous interval. So the left-hand end of interval number 2 is the right-hand end of interval number 1. So the left-hand side of interval number I would be at I minus 1, because it's the interval, the right-hand side of the interval before it. Okay, so to get to the beginning of interval number 2, I have to go 1, which is 2 minus 1. And this works even for the first interval, because 1 minus 1 is 0, so the beginning of the first interval is 1. And then even the right-hand one works for the last interval, because the last interval would be interval n, so it's 1 plus 3n on n, which is 1 plus 3, which is 4, as it should be. Awesome, done that well. So we've now done the part where we found the ends of our intervals, and the next part is to figure out the location of the maximum and the minimum. Okay, so in my old table, doing it with knowing what n is, I had a table of what the maximum was, where the maximum was, and then what the maximum was. So I need to know on every interval the location of the maximum. So on interval number I, location of the maximum is, well, now I need to think about my function. My function is increasing. It's a straight line with positive slope. So is at the right-hand side, since function is increasing. If it was decreasing, it would be at the left-hand side. That's where the maximum would be. Okay, so that's my description of where the maximum is. Now I need to know what the maximum is. So therefore, the maximum value on interval number I is, that's what we call capital MI, and it must be what I get when I put the right-hand end, no, it's on the, yeah, the right-hand end into the formula. But when I put that into the formula, it's 2x plus 1, isn't it? 2x plus 1. And now I have a formula for the right-hand end, for the maximum on interval number I, because I subbed in the right-hand end. Cool. The minimum would happen at the left-hand end, right? So on interval I, location of the minimum is at the left-hand side. So therefore the minimum must be what I get when I sub the left-hand side into this, which would be what I get for I minus 1. So you should always do whichever one has the I first and do the I minus 1 afterwards. So if the maximum value had been at the left-hand side, I would have done the minimum first, because that's the one that's at the right-hand side. Okay, almost there. So I've found where the maximum is and what the maximum is. I've found where the minimum is and what the minimum is. And now I can finally figure out what the formula for the upper and lower sums are. Incidentally, at this point, no, I'll do that later. So now I can say that the upper sum must be delta x times the sum of the capital MI's. And the delta x was 3 on n. And the capital MI was 3 plus 6i on n. And now I need to use the properties of how the sum sign works in order to calculate what this works out to be. So the sum sign can be brought in just like with expanding brackets. and plain numbers that do not involve I can be brought out. Okay? So I did two things there. I brought it in and did it by the 3 and that, but then the 6 on n came out of the sum. So that's n lots of 3, 3n. And there's a formula for this. It's a half of n plus 1. Those of you in AQMF get a cheat sheet. I'd write it on. Those of you in Maths 1A, you've got to remember it. Sorry. And now it's algebra. That n will cancel with that. That'll make that a 3. 3n plus 3n plus 3. So 18. No, I'm not going to skip that step. 3 on n times 6n plus 3 on n times 3, which is 18 plus 9 on n. That's the upper sum. Yay. The lower sum you would work out in a similar way. We can already see that the answer for the integral is actually 18, because if I make my number of subintervals more and more and more, it will become more accurate. And as n gets bigger and bigger and bigger, 9 divided by n becomes approximately 0. So the answer must be 18 for what the integral is. If the integral exists at all, the answer must be 18. For some very special and wickedly horrible functions, your upper sum and your lower sum will never get any closer to each other, and so the integral doesn't exist. So the lower sum would be delta x times the sum of the minimums. And the minimum, the delta x was 3 on n. And the minimum was 3 plus 6 I minus 1 on n. And this is where the fancy trick happens. Because it is an increasing function, the minimum on one interval is the maximum on the interval next to it. And so if you look at this, this is the same as the one we had before, except it has an I minus 1. So one piece of advice to you is that don't always do the upper sum first. Do whichever of them doesn't have the I minus 1. Do whichever of them has a plain I and not an I minus 1. Do that one first. Because the one with the I minus 1 you can figure out from the one with I. Because this is really beginning at 0. Because if I sub in 1, it gives me 0 at that spot. And it's really finishing at n minus 1. Okay. And, well, we know what it would be if it started at 1 and ended at n, and mine has just shifted back a bit, and so all the bits in the middle are the same. So the picture in my head, which I will always draw on my scrap paper, goes like this. I've got 0, 1, 2, n minus 1, n. And my lower sum is made of these ones, and my upper sum is made of these ones. Sometimes it's the other way around. Sometimes the upper sum is this one and the lower sum is those ones. So you can see they overlap in the middle. So if I were to subtract them, those bits would cancel out. So I didn't need to do any of this. I could have just said, all right, well, so, let's see if I've got this right. The upper sum minus, no, I'm not going to do that. Is it worth doing that? No. All right. Yeah, I'll do that. So the upper sum minus the lower sum, right? There'd still be a 3 on n, because that's out the front. and it will be, that's the upper sum there, which has all of them including n, and this is the lower sum here, which has all of them including 0, and I'll do this minus that, so it'll be all the ones in the middle will cancel out. So it will be 3 plus 6n on n, the one for n, minus 3 plus 6 times 0 on n, because that's the one for 0. Awesome. So 6n on n is just 6, so we get 9 minus 3. Is it? Yep. So that's how far apart the upper sum and the lower sum are. So for those of you doing or anything, if they particularly just asked you what is the difference between the upper sum and the lower sum, it would be completely irrelevant doing this, because you can go straight to here. You can say, if they just say, what's the upper sum minus the lower sum, then you can go, well, the upper sum minus the lower sum will be this. And you can skip all of that. Okay? Alright, so since the difference between the upper sum and the lower sum is 18 on n, therefore the lower sum must be the upper sum minus 18 on n. And so the upper sum was 18 plus 9 on n, and we take off the 18 on n. Which is in fact minus 9 on n. And conveniently, the upper sum and the lower sum, the upper sum is above 18 and the lower sum is below 18, which is exactly how it should work. So therefore we actually know, therefore, or not therefore, we say that for any n, the lower sum is less than or equal to the integral, which was from 1 to 4, was it? And that's less than or equal to the upper sum. So the upper sum, I've just put the formulas in, and the only number that is between those two values for every possible n is 18. So if you are asked to find the integral with upper and lower sums, you must put this final step in, because that's how you use the upper and lower sum to find it. That's finding upper and lower sums using summation notation. So I'll just go back through and point out the pieces of that. So first I divided the interval into subintervals and I figured out what the width of each one of them is. I figured out what delta x was. And then I figured out what the right-hand side and the left-hand side of each interval was. And then I figured out where the maximum was and what the maximum was. And then I figured out where the minimum was and what the minimum was. And then I used summation stuff to figure out whichever one of those included the I and not the I minus 1. And I started doing the ln up to here, and then I used this information to figure out how far apart the UN and the ln were, and that told me what the other one was. And then finally I was able to find the answer for the integral. So if you want to know what size n to use in order to get the error below a certain amount, then it's this information here. The error is actually half that, because the true integral is somewhere in between. You would normally use the average of the upper sum and the lower sum to estimate the area. And so if you think it through, the true area is here, the upper sum is here, and the lower sum in here, and that distance there was 18 on n. So we can't be any further than half of that from the real area. Because even if the area is... No, actually it's just 18 mm. Check your notes. You either divide this by 2 or you leave it as it is. So just check that out. Yeah?
Is it possible to use that method to find into turning points?
That has turning points? No. So someone says, is it possible to use this to find the integral of a function that has turning points? Yes and no. The answer is you have to cut it into each piece between the turning points. So this process will only work if it's an increasing or a decreasing function. So if it has turning points, you'll have to do this on one side and separately on the other, which is why we do integrals by doing the opposite of differentiation. Yeah, because this is too hard. Just we do this so that we can fully appreciate the wonder of not being able to not having to do this. So, yeah. All right. Any questions about upper and lower sums then? Awesome. So thank you. Those of you who are in AQMF can go if you want to, because this is now requests for Maths 1A.